I guess, with number 29 yesterday. You guys did a really, really good job with the Kahoot. Makes me feel a little bit more confident moving forward. So with the atomic number and the mass number, those two things you definitely have to keep straight, all right? So the atomic number, it's teensy tiny like the atom. It's the smaller number. It's only counting protons. You're only counting one thing. So if I'm looking out here and I'm going to count people that have only blonde hair. Okay, well that's going to be a few people. If I count people, hold on, you're exempt. If I count people that have blonde hair and brown hair, that's going to be more than if we just count the blonde-headed people. Do you guys agree? So if we're just counting protons, it's going to be less than if we count protons and neutrons. So that's why the mass number is always going to be your bigger number, because it's including two things, not just one thing, right? So as we look at, you're going to need to have your periodic table out, because for the first time, you're going to have to kind of look at it and find a few elements. We do have 3 or 4 videos today. Again, I apologize for you guys. You are my video group, so we're going to do those at the end. So we'll power through and do all the notes, and then I'll stop my recording and we'll get to your videos. And we have 2 songs, actually one of the best songs of the whole year, and then another really good one. So it's a really good day. Good Friday. Okay. All right. Good. So I see all the periodic tables out. So if you look at this, you might want to draw on here an equal sign, because the atomic number does equal the number of protons. That's the same number. Okay, so on your notes, on your chart, you might want to do that. I need to figure out my tech. I don't want to take the time right in a second to get my tools up when it's on this screen. I don't have that up, so I can't draw mine at the moment. But draw an arrow or an equal sign like right here, because the atomic number does equal your number of protons. Okay? And then if your mass number, maybe put a capital P and a capital N, because you're counting protons and neutrons for that. That's what that's including. Above your atomic number, maybe just write a capital P, because all you're doing is counting protons. Just to kind of help get you in mind. So on your chart, just like I have here for slide 30, capital P equals, and then over here for your mass number, a P plus N, because you're really counting up everything that's in the nucleus, the protons and the neutrons there. Okay? All right, one thing that we haven't talked about, how do we find the number of neutrons? Well, it's very easy. If you take a capital P plus N, right, which is your mass number, and you subtract your number of protons, which is your atomic number, you end up with your number of neutrons. If that makes sense. You're like, what? So your mass number minus your atomic number. And that will leave you with your number of neutrons. So that's how we determine this. Because remember, this mass number is going to be the big number on your table. On your periodic table, it has it down to like the 100th. You don't need to do that. You can round that mass number. That mass number is technically an average. What would be the mass number for any given element? We can just get rounded up to the nearest whole number. We do not need to go to the hundredths or tenths or anything. Whole numbers are fine. So this is going to be your big number, right? This is going to be your small number on the periodic table. All right, so the first one's done for you. If you find helium, helium is in the top right-hand corner, all the way up there kind of by itself. You should see that the big number is 4, The small number is 2. And so by default, if we know that the atomic number is 2, then the number of protons is 2. If we're assuming all of these are totally neutral, then by default, the total number of electrons would also have to be 2. Right? Because if you have 2 protons, you would need 2 electrons to cancel those out to make it neutral. And then how we got the number of neutrons, if you take 4 minus 2, you end up with 2 neutrons. And I promise you, this will become very easy and second nature very quickly. Seems a little like, whoa, there's a lot going on, but it's not bad, I promise. All right, so let's go to carbon. Find carbon on your periodic table. Okay, so what is the small number that goes with carbon? What is that atomic number? Okay. I think it might be I think it's a 6. It's very small. It's very small type, but it is actually a 6. I know. Yeah, it's kind of blurred together just a little bit. It is actually a 6. So by default, how many protons do we have?
6.
And how many total electrons then? 6. Okay? Now, let's go to, and I hope I have it, so we go to the mass number first. I can't remember if I fixed that or not. What is the big number?
12.
It's going to be 12, all right? So if I take 12 minus 6 to get my number of neutrons, okay, it's going to be 6. Oh, good. I couldn't remember. I didn't think I had it right. So our big number is 12, and this is protons and neutrons. So if I subtract my protons from that, I'm left with just 6 neutrons. Don't mess with me back there. All right. Now, how can we have something called carbon-14? We had carbon-12. Well, we're going to talk next about something called isotopes. So this is kind of leading into this. Isotopes, yes?
It's radioactive stuff.
A lot of times it is. Not always, but a lot of times it is. You're right. Isotopes are where you have a different number of neutrons than the normal. Okay? And so the number of neutrons can change, the number of electrons can change, and you can still have carbon. But if you change protons, remember it's permanent. Protons are permanent. So I have to still have 6 protons to make this carbon. All right? But that 14, it actually cheats, and that gives us what the mass number is. That's what this number that follows the element means. Not always will you see it written. Like, we really don't need to do helium-4 or carbon-12 because those are the normal. But if you're dealing with the isotope version of that element, then we put the mass number at the end so that we can determine how many neutrons it actually has. Because if we don't know the mass number, then we can't figure out the number of neutrons. So if this is carbon-14, the mass number is 14, right? And then we can figure out how many neutrons we have, because we can take 14 minus our 6. You guys following me? Yes or no? All right, so let's backtrack for just a second. How many protons are we going to have again if we have an atomic number of 6 still? 6, good. And then our mass number is going to be 14 because it tells us. Not because it says it on the periodic table. We don't have a special table that's just for isotopes. We know, and the only way we'll know, is if it gives us the name of the element and then it puts -14 or dash, something else, like uranium-238. We would know that that's the isotope version of uranium because it says 238 after the name or after the atomic symbol. All right, so we have carbon-14. So what's 14 minus 6? Or 14 protons and neutrons minus 6 protons. What do we get? 8. Very nice. Good mental math there. Okay. And that's as tricky as they get when you're dealing with the isotopes. So this is oxygen 16. Now, find oxygen on your paper. What's the big number for oxygen? I'm hearing some 16s, right? So is this dealing with the isotope of oxygen or just the regular? Just the regular, very nice. All right, so let's go back to the beginning so my order's right. How many protons are we gonna have there? Somebody maybe I haven't heard from, even though I really appreciate a lot of you trying to give me answers. What is the small number, the atomic number? Go ahead, Kate.
8.
Very nice, it's 8. And then how many protons are we gonna have, Abigail?
8.
And how many total electrons?
8.
It's hard to keep answering the same thing, but it's true, it's still 8. Okay, and then you already told me that the big number is 16, which is our mass number. And then we're gonna backtrack and subtract 16 total protons and neutrons from our 8 protons, getting how many neutrons? Good. So sometimes the number of neutrons is the same as protons, but the bigger the elements get, the more you move away from that. So sometimes they're the same as your protons, but it's not like a set rule. So you can't just be like, oh, however many protons you have, that's how many neutrons. That's not a thing, right? As nice as we would like to make that, it's not true, all right? Okay, so let's take a look at isotopes now that we kind of introduced them. They're atoms of the same element, but they have a different number of neutrons. I will tell you, for whatever reason, isotopes and ions tend to be 2 vocab words that people mess up for a while. I usually put those 2 questions on like 3 or 4 units from now. I'm still asking for you guys to be able to tell me what an isotope is and what an ion is. We'll talk about ions in a little bit. But isotopes, it's a weird word. I think you guys just mentally like like block it out. So maybe you guys will be the first group in a while that that's not true for. But a lot of times people struggle with isotopes. All right. So just kind of maybe mentally like make a little like star or like like pay attention. Like when you see isotopes, really try to focus on what they mean and like what it is so that you aren't still struggling with it here in a couple units. Yes, sir.
I would probably pronounce it isotopes.
I know, it's spelled weird, it's pronounced weird, it's just all kinds of weird.
That way
Okay.
you can remember that.
So different isotopes actually have different properties. So carbon 12, which is the normal carbon, and carbon 14 are slightly different. They're still carbon because they have 6 protons, but they react different chemically and they kind of behave differently. So the name of the element is followed by the mass number. So like carbon 12 is the normal, carbon 14, saying that, we know that we're talking about an isotope. So uranium-235 and uranium-238. This is the isotope version, this is the isotope version of carbon. So the average atomic mass is the average mass of all the isotopes of an element. So this isn't something that you really need to worry about too much, but again, this is why on your periodic table, some of those mass numbers are decimal numbers. Like if you're getting into like real legit hardcore science, you're gonna need to be that specific, but for what we're doing, again, this is a nice introduction, and I don't even believe that in chemistry with Miss Durchie, you guys break it down where you need to worry about going to the 100th. We just need to deal with the mass numbers as whole numbers, and that's fine. And that's all that's saying. So here we have hydrogen. These are all hydrogens because they have 1 proton. So that 1 proton identifies them. Remember, protons tell you, it's like the fingerprint, right? It's the permanent number. If I change my number of protons, I'm gonna change what I'm dealing with. If I go 1 more proton, now I have helium. If I add 1 more, now I have lithium, okay? So here's 1 proton, and 1 proton, and 1 proton. Here, there's no neutrons at all, which is a thing. This is called protium. This is deuterium, where it has one neutron, and this is tritium. It's just special names for for this hydrogen, these hydrogen isotopes. Okay. If you look at your periodic table, hydrogen has one proton, of course, and then it also has one neutron. That's, a mass number of one. So this is the normal version of hydrogen. And the reason I know that is because on my periodic table, it has an atomic number of one and a mass number of one. If you notice, that's the only one like that. Okay, so it's the only one that doesn't naturally come with a neutron, right? And I'm not gonna ever really ask you that. This is just to kind of visually see. So isotopes are atoms of the same element, all hydrogens, but they have different numbers of neutrons, 0, 1, and 2. Okay. So this would have a mass number of 2, and this would have a mass number of 3. Right, we're getting technical. And we will come back and watch that brain pop again at the end. All right. So this has all been leading up to the main event for this unit, which is the periodic table. So you had to understand what the information on those little squares and tiles meant, atomic number, mass number, the atomic symbol, before you could understand the arrangement of them. So that's what we're going to get into next. So this is an organized and systematic way to predict, and predictable way to display all the known elements in our world. Right? It's not just random. It's not like taking all these Scrabble pieces and like throwing them up there and then that's what you go with, right? Back to that in a minute too. And so Dmitry Mendeleev, he was, I believe, Russian, if I'm thinking right. He was the first one to develop a periodic table, and he organized the elements according to property and mass. Pretty logical, like he had a system in mind. And the modern table, though, is arranged according to increasing atomic number. So you go 1, and then all the way across to 2, and then 3, 4, and then 5, 6, 7. So it's going up by protons as you read it left to right. So just like you would naturally read a page or a paragraph, you start on the left, go to the right, drop back down, go to the next line or row, and keep going across. And now that's how the periodic table is arranged with those, going from 1 proton to 2 to 3 to 4 to 5 to 6 to 7 as you go across. And this is something that's called periodic law. When the elements are arranged in order of increasing atomic number, there is a periodic repetition of physical and chemical properties. And because it drops down and forms a new row when it does, all of the things that are in, all the elements in a certain column are going to have similar characteristics. Okay, and so that makes it kind of easy to keep track of certain things. All right, so groups, they're also sometimes known as families, but I want you to focus in, see this word up? It's in the word group. I have to give credit to a student, Spencer Bartow, years ago. He's the one that said, he looked at it, he goes, well, up is in the word group. I was like, dang, it sure is. And so it's a real easy way to remember that these are the ones that go up and down, okay? They're the vertical columns. Group actually has the word up in it. And so they're organized by similar properties that we'll get to next week. And they have the same number of electrons in their outer energy levels. So you might not understand exactly what that's meaning right now, and that's okay. We'll get to that next week. But just know that all of those have similar electrons. And each of those levels can only have a maximum number of those special electrons. And so each row is going to end when that energy level gets full, and then they have to drop back down and go to the next level. And then you go all the way across, and when the energy level gets full again, you drop back down and like start another line or another row. And again, we'll get to that more later. And we'll use something called electron dot diagrams to represent these outer electrons. And the reason they're so important is because these are the ones that can interact with other atoms because they're on the outside. Don't let this overwhelm you. It might be like, whoa, there's a lot. It'll all make sense when we put it all together. Okay, and then we have the periods. These are the horizontal rows. Think of reading a sentence left to right. It ends in a period, right? And so you're reading horizontally or left to right. And so the periods, are the ones that are going left to right. They're organized by increasing number of protons. So as I go hydrogen 1, helium 2, lithium 3, right? You keep adding protons as you go across and then drop down. We classify these not by electrons, but by characteristics. So there are some that have metal characteristics, some that have non-metal characteristics, and some that have characteristics of both, which are called metalloids. Okay. And so you can think of the groups and families as the vertical columns, kind of like the pillars or columns on a White House, and they're classified by electrons. They go up. Our periods are the horizontal rows. If you think of rowing down a river, you're going to row left to right. You're not rowing up and down, right? That wouldn't make sense. So rowing down the river, horizontal, and we classify these by protons.